And I'm gonna share my screen. All right, can everybody see? Cool. All right, so this is very Flatiron template, but cool. We're gonna talk about recommendation engine today, and let's see, Michael's joining. Hey, Michael. All right, we just got started, so we're good. So we're gonna talk about recommendations engines today, and this is kind of split into three main parts. There are different kinds of recommendation engines. There are concepts behind each kind of engine, and there are pros and cons of the different times, and like we're going to talk about when to use which. The way the labs are set up is slightly different from the structure that I'm going to present the material. So hopefully it like kind of complements each other, I hope. Awesome. So types of recommendation engines and also why. Can you guys just like think about what your favorite application of a recommendation engine is? Like I'll start with mine. I actually really like Facebook ads. I almost exclusively shop off of Facebook ads. I think their targeting is just so great. So I really like Facebook ads. Any others?
I got engaged and was engaged for a while from meeting someone on OkCupid. And it didn't work out, but there was some good times. So I guess the algorithms are pretty okay.
Yeah, so yeah, recommendation systems and sorry, dating apps algorithms are actually very similar to one kind of recommendation system that we'll talk about as well. Anyone else?
I like Spotify a lot.
Ooh, Spotify is a really cool one. I actually like read a little bit about how Spotify works. I can talk about that later.
Me too, Darius. I use that one a lot.
Yeah, awesome. Cool. So in terms of recommendation engines, there are three main types. We have non-personalized, content-based, and collaborative filtering. So most of the recommendation engines that data science students end up building are the last two. So it'll be either content-based or collaborative filtering. So which one you end up doing is kind of determined by the data that you have, and we'll explore that a little more later. And so why do we need them and what are some examples? We've gone through examples earlier, and we need recommendation engines just to know what to do, you know, make money as well. Yeah, cool. So to start with non-personalized recommendations, let's see, something like a non-personalized recommendation would be just like simply recommending like the top rated items. So like if you have no data on your customers or any of your products, you would just return the top rated items. That just makes sense, right? Like you know that historically something's done well, so there's a higher chance that your customers will like this item. In a very, very similar vein to that, most bought, watch, consume items. Like there's a reason why on YouTube there's a whole tab on like trending videos because people care about what's popular. Another thing is highest ROI. ROI is return on investment. So obviously, if let's say you're selling something, you want to recommend things that give you the highest profit. And that is definitely a strategy that newer companies use as well. And so the simple pros of non-personalized recommendation engines is it is easy to make recommendations, right? You get to choose what products you're going to push out. So it's really good for new businesses. Let's see. Yeah, it's really good for new businesses when you don't have much data on content and users, and also when you really want to push certain items. Prime example is when you're, let's say, a brand new user of YouTube, you immediately get recommended the top trending videos at the time. So that's a very, very straightforward example. A lot of times people will start with non-personalized recommendations, especially if you're a smaller company. People would start with non-personalized recommendations, gather feedback on how people like these recommendations, and then they can slowly start to build their more advanced recommendation engines. So you're sort of using this as a tool to start to gather data. Cool. Any questions on this? Because this is like the most straightforward one. We can move on really quickly. Awesome. So next we're going to talk about content-based recommendation engines. So content-based recommendation engines and the stuff that, and the technology that you would use to build content-based engines is actually not very different from stuff you already know. So in short, content-based recommendation engines make recommendations based on an item's features. So by features, I'm sure we're familiar. Let's say we have movies, a bunch of movies, each row is a movie. Features of movies would be like the genre, actors, directors, the year it came out, and rating, so on and so forth. So the data that you would feed into a content-based recommendation engine would look something like this. And models we already know can do this. So question I'm going to pose to you, like based on the stuff that we've learned already in like mod 3 and maybe mod 4, how would you build a recommendation engine using models already know? And like feel free to like come up with your own like ideal world data that you might use for a recommendation engine.
Well, I'm just going out. I'm gonna
Go.
movie with your movie idea.
Mm-hmm.
You could just use like a random forest and extract the 10 top most important features, right? And just go that way from there, just as a base. I don't know how in depth I could take this idea right now on the spot, but that's a thought.
Yeah, that's a really great idea. So I guess to like further flesh out what you're saying about like taking like movies, let's put it in like a more recommendations system specific context. If let's say we have like user X and we want to recommend user X a bunch of movies, one of the simplest ways to do that is just look at the movies that user X has already seen. Perhaps like, again, use like a random forest or a classification model to, you know, classify these movies. Like based on, you can build a model saying like, okay, will user X like or dislike this movie? Or you wanna go even more in depth, you can build like a regression, like seeing like would they rate it like between 1 star and 5 stars, how would they rate a movie? Those are like existing models that we know that we can use to build content-based recommendation engines. And that is very, the situation where you would do something like this is if you have a lot of data on a single user, which sometimes you might be able to find. I know like in the Yelp data set, there's like one user that's like reviewed like 50,000 restaurants or something like that. So you could do that. Yeah, it's pretty wild. But yeah. Any other ideas of like other algorithms that we've learned and how we can maybe create a recommendation system? Like just changing the context of how we use some models that we already know, how we can build something that could recommend something.
Kind of when you were mentioning about like a dislike or like, it made me think of like a logistic regression, to where like each of the columns or features would have a weight assigned to them, and based upon that user, you get like a probability, I guess, for them.
Yeah, absolutely. So any content-based recommendation engine just uses feature data. So any model that you build using feature data of like the items that you're recommending is considered a content-based recommendation. So like classification model using logistic regression, absolutely. It's another form. It is a form of a content-based recommendation engine. Actually, the most straightforward content-based recommendation engine is using nearest neighbors. So do we remember like k-nearest neighbors? So in k-nearest neighbors, it was a classification algorithm that would classify points based on like knowing which classes the points around it are. So let's say we have like 10 points in space. I have this new test data. I'll see like, okay, nearest to this test, what is the nearest neighbor to this test data? And if k equals to 1, we'll classify it to the same class as whatever the nearest point was. Very briefly. But the thing about k nearest neighbors is you sort of are calculating a distance between points. And so the most typical and like the easiest to build content-based recommendation engine is let's say you have all this feature data and they're all like represented numerically. Let's say we know that I like the movie Star Wars episode, I don't know. I think people like episode 5 a lot. I don't know. But let's say you like Star Wars episode 5 a lot. You would then look into your data set, find episode 5, look at those numbers, and all you have to do is compute the distance between episode 5 and every other movie in your data set and just recommend the closest ones. Does that make sense? Yeah. So there are also different ways you can tune it. You can take in not just one movie, but you can take like an average of a bunch of movies and turn that into like, you can just literally just add the numbers together and add the vectors together and like form its own vector and then find the nearest thing to that like combination of movies. That also works. I actually in the past built a board game recommendation system where I scraped like most of this. Have you guys heard of Board Game Geek? Really great website if you're into board games. I'm not, but whoever I was working on the project was. And we built like a recommendation engine which would take in your like 3 favorite board games and recommend you something new. And the thing about these content-based recommendation engines, it's like really simple if you think about it, because you're doing like nearest neighbors. And then if you want to ever filter your recommendations, you can filter them based on any of the features that you already have. So let's say you want to make a recommendation based on Star Wars, but you want to like filter out, I only want comedies that are similar to Star Wars. So after getting those like nearest neighbors, I can then filter out the data frame of like distances, sort that, and then figure out which ones are the best comedies that are also somewhat similar to Star Wars. So that's a really cool way to, I think like the easiest application of a content-based recommendation engine. Also, you can use clustering, and clustering sort of like simplifies your recommendation process. So if you have a lot of items, just imagine like you can cluster them, and then based on like your input data, so you say, let's say you know this person likes to buy bags, based on your cluster data, you would only measure the distance between bags. So you don't have to worry about like maybe 80% of your data. So you would use that in conjunction with the nearest neighbors model that I had mentioned earlier. Finally, you can also use neural networks. There is a really great library, and I'll link it to you later. It is called Annoy, and it's created by Spotify. And it's basically it's an extension of nearest neighbors model where it kind of fuzzy matches. So it intentionally throws in things that you might not expect, which is why I think like Spotify's algorithm is really good for discovering new music. So that's a really cool algorithm. I will send out their GitHub later. But how you can use a neural network to make recommendations, I think a good example is, let's say you run like an online store selling a bunch of clothes, and you know that someone likes, I don't know, pink dresses. You can actually run a similarity between all of the images that you have of all your clothes and recommend similar images. So you would do that with a CNN. And there's a technique to that where instead of like using a CNN to classify, this part might not make as much sense if we're not familiar with like CNN architecture, but you just take off the final like classification layer and you have like embedding. So each photo would be represented by like a vector. And then you can just find like, again, it's like the nearest neighbor of these vectors. If anyone wants, I have past student projects who have done exactly that. So let me know and I can share. But cool, yeah, those are like basically content-based recommendation engines use a lot of the models that we already have learned. So I won't go too much into that because the next thing is super interesting. Ooh, and before I get into the next thing, there's also similarity metrics, which is key when we're talking about like nearest neighbors. Like, how do we define what is nearest? So the one that we're most familiar with, I think, is Euclidean distance, which is like the Pythagoras theorem, and it extend into multiple dimensions. There's also cosine similarity that might make sense. It like looks at the angle between vectors in space. If that doesn't make sense, don't worry about it. Correlation is actually, interestingly, a really, really good similarity metric. Good in the sense that it has proven in existing models to be the one that's most effective. Why mathematically, no one has found out yet, but it just so happens to be that a lot of the models that use Pearson correlation happen to be better. So it's just demonstrated experimentally to be better. Cool. So pros and cons of content-based recommendations, really quick. This is kind of funny because I once bought a plant from Amazon. I'm not a plant person. I want to be, but I'm not. So I killed that plant. But recently I've been seeing a lot of these ads where they keep recommending me plants. So that could be like either a pro or con of recommendation of a content-based recommendation engine. So like in another context, if you like horror movies, a not so great recommendation engine might end up only recommending you horror movies. There is also something known as a cold start problem. And the thing about content-based recommendation engines is that you don't have that problem. So let's say a cold start problem basically means that if you have a new user and you have no data on that user, some algorithms you have this cold start problem because you don't know what to do with this new user. Like you don't know what to do about like, how do I treat their no data? So with a content-based recommendation engine, you just need the person to like maybe click on one thing and it's very easy to start making recommendations right away. Cool. Any questions about this? I know I like dumped a lot of information out, but it is very simple. It does use a lot of the models that we've talked about before. Awesome. So the third kind of recommendation engine is collaborative filtering. So whereas in content-based recommendation engines, we were using the typical like feature data frame where we have like rows being the data points and the columns being features. In collaborative filtering is a little different. We have something called a utility matrix, and it's like very key to collaborative filtering. So a utility matrix, this photo will make things a little clearer. So a utility matrix basically shows the user ratings of different items. And it's usually sparse because not every user would have seen every movie. And so the idea here is to fill in the blanks and then recommend the items with the highest predictions. So the numbers might be a little small, but let's take a look at user one. So user one has seen movie 1 and movie N, rated it like a 1 and a 3. Through collaborative filtering, we want to fill in these blanks. And so the blanks happen to be filled up with a 4 and a 2. Therefore, we're like, okay, there's a good chance that user 1 likes movie 2. So we're going to recommend movie 2. That's kind of the idea of how collaborative filtering works. And there are different ways to do collaborative filtering as well. And I'm actually going to go through a bunch of them because this is the algorithm that like ruined my final project for me because I just got so obsessed with learning about how it works. So please let me know if I go like way too in depth.
Yeah, was this the part where, because I started on this section, but I didn't quite finish it, but was this where you look for commonalities between users and if user 1 and user, well, if they both like the similar things and rated them similar, then they fill it in accordingly.
Absolutely, absolutely. That's exactly how you want to think about this. So you're making recommendations based on how users have rated items. So basically, yeah, do I have an analogy here somewhere? Yeah, I don't have my analogy here, but basically if like, I know, like if I like the show Friends and my friend likes the show Friends and I also like Parks and Rec and my friend's like, what show should I watch? I would recommend Parks and Rec because I know that we already like something similar. Cool. So there are 3 methods to do collaborative filtering. There is memory/neighborhood based methods, and I will go through one of them because they're really just the inverse of each other, and we'll see why later. And then there's also model based, which is matrix factorization, which is that is the algorithm in my opinion. Cool. So really quick, we're going to go through how you do collaborative filtering by doing user to user similarity. It's going to get a little mathy, but hopefully I can explain it well. All right, there's a lot on this slide, but let's not freak out. So here I have this utility matrix of 4 users and 4 items. For this example, let's say that every user has rated and watched, has rated every item except for user 1 and item 3. And we basically want to figure out what that rating is. We want to find out what user 1 has rated item 3. So using user to user collaborative filtering, you're comparing this matrix on a user level. So first step, you want to get user similarity values. So because we're trying to fill in the blank for user 1, we want to see how similar user 1 is to all the other users. So here we have user 1 and user 2, 3, and 4. And these numbers are just the cosine similarity. This one I just chose cosine similarity. You can choose whichever one you want. And these are the cosine similarity values between the users. So it's 0.65, 0.76, and 0.83, and this sums up to 224. Why we sum this, we'll get into this later. Second step is to just get the predicted rating by taking a weighted average of all the others' ratings of item 3. So we have these similarities. Now we want to see what the other users had rated item 3. So the multiplication we're doing here in this equation is we're taking the similarity multiplied by the rating. So here we see how for user 2, it's like a 4 and then 0.65. So that's what this first part is. And then similarly, we have 5 multiplied by 0.76 and then 4 multiplied by 0.83. And we're taking a weighted average. So that's why instead of just dividing it by 3, we divide it by 2.24. And so we end up with a predicted rating of 4.34. Does that make sense? Yeah. So that's just like coming up with this predicted rating based on user similarities. I guess, oh wait, before I get into that, some pros and cons. It's highly personalized. However, it is computationally heavy because even with just this 4x4, we did a bunch of computations, right? First, we had to find like the similarities between the target user and all the other users. And also we had to like come up with this weighted average. So it is more computationally heavy than, for example, just, taking like the distance between items themselves. There's a popularity bias as well. So imagine if like item 3 was just rated 5 across the board. Very likely the prediction is going to be something high. So if you ever had an unpopular opinion about a movie or something, that's not going to account for that as much. Finally, you have the cold start problem, which was what I was talking about before. Imagine if user 1 had no data, there's no way to compute a similarity between user 1 and another user. So that's what I mean by the cold start problem. If you're using something like collaborative filtering, you just can't, because you can't compare the user or the item, which we'll see later, to anyone else, and you just can't use the algorithm because you just don't have the data to do so. All right, those are the pros and cons. Item to item collaborative filtering is exactly the same, but instead of doing the similarities for users, you're doing the similarity for item. And so you see here, pretty much the same thing, but just on a different axis. We're doing item 3, so therefore we're combining the similarity values for 3 with 1, 2, and 4. And then the prediction is taking the weighted average that way. So the math itself is exactly the same. You're just like doing it on a different axis. You're doing it for items instead of users. Cool. So that's like a really it's a simpler way to do collaborative filtering. So user to user versus item to item, which is better? Item to item has proven to be more effective because it's harder to predict users' unique tastes. So if you think about it, if you're like comparing users, it's harder to extract like unique ratings of items that way. It's kind of hard to think about it. I actually linked a really great chapter of a textbook if you're really interested in this. You can go down that rabbit hole, but yeah, they explain it really well. But item to item has proven to be more effective. In terms of time complexity, which is something you might want to take into consideration when you're choosing which direction you want to do, user to user is m squared by n, because first you're doing the similarity between them, and then you're doing that weighted average thing. And item to item is the other way around. I don't know if you guys have ever talked about big O notation at all. Maybe like, okay. Yeah, this is something that's good to know and get used to. Is just talking about like, if let's say I'm running a for loop on like something that is like on a list that's 100, length 100, it seems to run pretty fast. But if you want to run this for loop on something that's like 10 million, that's maybe not the most effective thing. So there are actually algorithms that run slower, the more, as in not slower, but like it runs more efficiently the more items, the longer the length of whatever it is you're looping through. So complexity is a whole nother topic, but definitely good to like look up maybe after graduation. So we'll not talk too much about that. And yeah, I think I said earlier, experimentally, Pearson correlation just demonstrated to be the best. All right, so my favorite part, model-based collaborative filtering. So the way that you do model-based collaborative filtering is by a model called SVD, which stands for singular value decomposition. It is a linear algebra technique, and it is another way to fill in the utility matrix that is actually a combination of the two methods that we talked about earlier. So it's kind of a way that they combine both user to user and item to item. So this is going to get a little linear algebra heavy. I don't know how your linear algebra, how you guys are feeling about it, but I'm going to try and like talk through it because I think it's really, really interesting. So the idea of how SVD works is it does matrix factorization. And I don't know if you remember like back in like high school math, when you were asked to like factorize a quadratic equation, it's basically representing like a quadratic equation as like a product of two parts. So you would take like x squared plus 2x plus 1 and represent that as like x plus 1 multiplied by x plus 1. So that's the idea of factorization, like breaking up something into parts. So what matrix factorization is doing is taking a matrix and representing it as a product of two matrices. And I'll talk about latent features later. It's actually something that's PCA related. And then it does gradient descent using this alternating least squares method, which I will actually walk through later if we aren't bored by all the math. And it's very, yeah, it's kind of math heavy, but the best in class models use SVD. I think I mentioned this at like office hours previously, but there's like this Netflix prize competition where they used to hold this back in like the late 2000s. And there was this model created by this guy named Simon Funk. He was the creator of SVD, and he won that competition, and he was predicting Netflix users' ratings of movies to an accuracy of like 96% using this exact algorithm, which is super cool. So we're gonna start from a high level. We have the same utility matrix as before, and we're breaking it up. We want to represent it as a product of an item matrix and a user matrix. How much do we remember about matrix multiplication? Little bit? Okay, cool. So as we remember with matrix multiplication, if we multiply two matrices together, the product matrix is gonna be of the dimension of however many rows the first one has, multiplied by the number of columns the second one has. So that's why for this, it always has to have like 4 this way and then 4 this way for the user matrix. The dimension of this, like, and these are latent features, is basically they're doing like a form of PCA on all of the items and all of the users. I'm not gonna go super into this, but they're basically representing the item as a vector of numbers. If you're interested, definitely read the textbook because it's really cool. It's like they're kind of doing like reverse PCA, because whereas here you have like one number, they represent it here as like 2. And basically why these cells that are highlighted yellow, these 4 values here are what affect this value. So if you think about it, when you're multiplying the matrix together, this value here is the dot product of this and this, if we remember matrix multiplication. All right, cool. So basically, we do gradient descent. If you remember how gradient descent starts, you always start with some initial values and then you like just get better. And so with gradient descent, in this case, we're just gonna choose like an arbitrary, start everything with 1s. And so the idea here is what we're trying to do is we're trying to reconstruct the utility matrix. We're not trying to just fill in the gaps, because using linear algebra, there's really no way to fill in the gaps. But what we're doing here is we're going to reconstruct the utility matrix as best we can by creating these new item and user matrices. So what we're doing is we're trying to get this to be as close to this as possible. And so the values that we're going to be changing during our gradient descent are all of these values, these 8 and these 8 here. So these 16 values are what we're going to change. So if we initialize all our values here as 1s, if you do matrix multiplication, this ends up as a grid of 2s. If you just like break it up and do the multiplication, it comes up to 2s. And the cost function that we're trying to minimize here is RMSE. And so this RMSE is basically calculated by looking at each corresponding cell. So here we're looking at the error between like 2 and 4, 2 and 2, 2 and 5. And we're just gonna add, like we're just gonna root mean square those errors across the 15 cells. So excluding this question mark. That makes sense? Yeah, cool, awesome. So the idea is we're gonna change these values to update these values to be as close to this as possible. So how we do that is, it's actually pretty interesting. We first start with, okay, what is the best value for this yellow square right here? And it's actually a pretty straightforward optimization. I don't know how familiar we are with like calculus, but if we have this value to be x and we multiply it out, so changing this will multiply x and 1 with all of these. And so this matrix becomes just like a row of x plus 1 at the top. And so with this, we can actually find what the best value for x is, because we can find out what the lowest RMSE across this top row is. So because the only values that we're changing by changing this one value are these like top 4 values, we can just compare these top 4 numbers with these top 4 numbers. And that's what's happening here. We're taking like 4, 2, 3, and 5, which come from here, and taking each of those minus x plus 1, and then taking the square, which is kind of how we can do like a root mean square. And then if we set the derivative of this to be equals to 0, we find that the best x is 2.5. So the best value for this cell over here is 2.5. So setting that as 2.5, after we do the matrix multiplication out, this whole top row becomes 3.5. And you see, as a result of updating that value there, RMSE goes down from 1.75 to 1.58. And so this process of alternating least squares happens over and over again for all the values here. So all the ones, you're going to keep doing that. And not just once over, because once you change one of them, the relationship between all of them, like 2.5 might not be the best after you update all the rest of them. So you're going to keep doing it over and over again. Those are like all your gradient steps. And you're going to end up with something that looks like this. And honestly, what this is, it doesn't matter. What matters is this. So this is the best constructed utility matrix that closely matches this. And so that process is just repeated over and over again. These keep changing, and therefore this keeps updating to become as close as possible to our original utility matrix. So as you can see, it went down from 1.75 before all the way down to 1.15. So basically what that's saying is that on average, each of these ratings is about 1.15 off, and it's on a scale of like 1 to 5. So depending on context, that could be good, could be not good. So something that's really cool about this algorithm is that every time you update one value, it changes an entire row, right? Like changing this to 2.5 changes this whole thing. If you were to change this first value here in U1, it's going to change this whole column. And so this algorithm is really cool because it's what's called parallelized, where it takes into, it like tries to preserve the relationships between rows and columns as much as possible, because every time you're changing something, you're changing an entire row or an entire column. So therefore it's taking into account the similarities across both rows and columns. So that's what's like particularly, I guess, mathematically elegant about the algorithm.
Like a super, super intense Sudoku game.
Absolutely, yeah. And so you can like keep doing this over and over and over again. I think like in your, when you do surprise, you like tell it where to stop, just because you can always get something. I think you can pretty much always get something better. But yeah, so that's how you end up at a prediction of 3.7. And interestingly, if you remember like the two methods before using this SVD method, so this is 3.7. If we go back to item predicted 3.3, and user to user predicted 4.3. So the SVD number happens to be in between user to user and item to item, because it's taking both of them into account. So that, I think that's really cool as well. To be honest, the math of it is not super important. I would just say if you do end up using this in your project to at least like get some idea, like use keywords like alternating these squares or like updating rows and columns and parallelizable, because it could be something that I have had like a classmate, one of my classmates was actually asked in an interview how it works and he had no idea. So that's how I started obsessing about this. But yeah, that is how SVD works. And yeah, that's pretty much it for rec systems. I can also go through, actually, yeah, I'm gonna do that. I'm gonna go through really quick how you would implement. I don't know if you guys have like tried out the surprise labs on Learn yet. Maybe, okay, yeah. So let's just go really quickly. Again, as I said, like my packages don't work, but there are certain things I think are important to explain. These are the usual things that you import, and I just sent this out to your channels as well. But anyways, I'm using a built-in data set, and here we're gonna look at movie predictions. So there's this data set object that you can load this ML100K data set, so that's what I'm doing here. Please, by all means, if you want to like use this code and like run this yourselves, please do. But anyways, pretty much the same thing. You do your regular train test split. One thing to actually note, which kind of annoying, Surprise has its own train test split. I think it throws you an error if you try to use the regular scikit train test split. Very straightforward. You instantiate your model, do your dot fit, and then you do your dot test. And then you have your predictions. And then with this code, you can just see like with a given user and a given item, what is the estimated rating. Cool, so that part is pretty straightforward. What I wanted to bring up is if you're using your own data, and here I have, and it's also in the zip file that I sent out, I have Yelp reviews. And basically because of the way collaborative filtering works, you really only need like 3 columns of data. You only need like user IDs, item IDs, and then ratings. So this Yelp review CSV, let me see if I can just like pull it up here. Yeah. Unfortunately, I can't show it, but it's just user ID, business ID, and then the number of stars. So this is exactly what your data frame should be looking like. The irritating thing about surprise, unfortunately, is, here I have a little bit of ED, but let's not worry about that, is that when you use surprise, you have to feed your data into this reader object. So the purpose of this reader object is that it has to, that's where you tell it what the scale of your ratings are. So it doesn't blow up your ratings like under 1 or more than 5. So that is important. So that's why you have to use this reader object first, tell it what your rating scale is, and then you can load from your data frame. And here I had done this and assigned it to the variable Yelp. And it takes in this particular order, the user ID, the item ID, and then the ratings columns. And then you feed it into the reader object. So this is something I just wanted to highlight, that if you want to use surprise, you have to unfortunately feed your data through this reader object. And then the rest of the stuff is all the same. Something else to mention is some of the hyperparameters that you can tune. The usual ones like number of epochs. This is learning rate, and also regularization is available. So those are things that you can tune. This part, N factors, actually refers to the number of latent factors. So if you remember like this stuff, like the number of like columns here and the number of rows here. So that's what the latent factors are. So tuning that apparently also, I think if you like give it more latent factors, you kind of like overfit it a little more. But yeah, that's definitely something you can tune as well. But other than those little minor things, it works just like any other scikit model that we've already used. One last thing to mention, I also let's see. Oh yeah, this is the book chapter I was talking about that like really started me on this like rabbit hole fun journey. Surprise, the documentation is actually pretty good. They provide you with a lot of starter code. LightFM is another library that allows you to do hybrid recommendation engines. So if you happen to have both, you have both like rating data and also like content-based data, you can put them both together, and then you can like deal with like how much you want to weight each of them using LightFM. It's actually really, really cool. Again, I have sample projects to show how they work. And then I also turned this lecture into 2 blogs. if it's easier for you to like read stuff, I have that there. But yeah, that's about it for recommendation engines. Any like overall questions, thoughts about maybe how you might want to use it in a project?
Yeah, I was thinking of, would there be any realistic way to pull together like 2 type of rating information, like from like Spotify or YouTube, and like recommend something else, I guess?
Ooh, like let's say you're taking like data from Spotify and like based on like your Spotify activity, recommend like a YouTube video. That's definitely possible. I have seen like one project that, not one of my students, but like another like cohort students I've seen, was they used like Goodreads reviews, like a user's Goodreads reviews about like books to recommend movies. That's definitely doable. You have to like really think about the data that's available to you and how you want to, and that's probably going to be something content based, how you want to take that information, how you want to represent that as like how you want to use the data basically, and how you want to sort of make that connection between the 2 different things that actually can be pretty cool. Definitely possible. I don't know too much about like the Spotify YouTube connection, but if you have an idea, I'm happy to talk about it. Yeah. Anything else?
You know, I was thinking at one point, I was considering making a recommendation system. So I teach spin classes, and I think sometimes the hardest part is putting together a playlist based on beats per minute. So I was thinking I could build something to help me throw together a playlist based on beats per minute
100%. Like, for example, like if you want to maintain like a particular beats per minute, very straightforward content-based rec system. You can just like pull from Spotify. And Spotify actually lets, I think their API lets you do like a search. So you can filter by BPM, and then let's say you have an existing like few songs that you really like. All you have to do is just query the API for like a bunch of songs in that genre, and you can find the songs most similar to like the songs that you really like, and then those will probably have very similar vibes.
Mm-hmm. And I've already like categorized them. Like I already have some playlists that are based on like climbing or sprinting or whatever. So I could like train it based on that.
Yeah. And like, again, like with content based, you can really like filter out your recommendations because you are really computing a distance between whatever you have and everything else. So all that is, you have that like distance metric. All you have to do is just sort that and just take the top of whatever you want. And so like the outputs are really, really easy to get.
Future goals.
Yeah. Content-based rec systems are actually very doable projects. Those are the projects that like you can get your first pass done really fast, but tuning it and like making it give you like the results that you really want, that's the part that you end up spending a lot of time on. Yeah, because with those you can play around with, oh my gosh, do I want to weight like maybe the key of a song higher? Do I think like, I know like Spotify has this metric called like danceability. Do I want that metric to be weighted higher? So you can decide like what is more important, and you can really like go in and like literally just like multiply a column by 2 to make it more, make it a stronger variable. Content based is a lot of fun to play around with. Awesome. Any last questions? Awesome. Let me just stop this recording.